Okay, very happy to have Bo Wagner here today. He's currently a postdoc at Penn. He was, before that, he got his PhD at Harvard. He went to undergrad at Duke. He's actually been an intern at MSR in New England and an intern twice at Google. He's also a really,
yeah.
my cheat sheet. Also a really serious runner. He even won like a ACC award for best scholar athlete of the year. So looking forward to your talk today, Bo.
All right, thanks. Yeah, thanks very much. Thanks for coming to the talk and putting this together, especially thanks to Alex for making it happen. Yeah, I'm really excited to get to talk to you guys. So yeah, so the title of this talk is Acquiring and Aggregating Information in Societal Contexts. So I want to think about a paradigm that's very familiar to many of us, especially in machine learning, right? There's a bunch of information, we feed it into our algorithms, and they output predictions or decisions, right? So it might be data about the weather, and the output might be some classifier that classifies whether it's indicating sunny or rainy for the next day or whatever. Okay, but well, we traditionally like to analyze our algorithms with this sort of perspective. Actually, there's this recognition that they live in a context that's bigger than this, right? So a context of people. In particular, the data that's coming in is data that comes from people, the data maybe about people in some way, and the outputs, the decisions or predictions, also are affecting people. So this raises some really interesting questions, I think, both from a societal standpoint. So how should these be designed when we're taking into account this context? And there are often really nice technical questions, which I really like, coming from more of a theory background. So first, I just want to tell you briefly about the kinds of questions that come up, and then which ones I'll be talking about today in more detail. So I like to break the challenges down into three rough categories. So one is strategic behavior of agents, right? So when you take some like machine learning type system and put it in a context with people, they may be behaving strategically, and so this input data you're getting, for example, might not be the sort of real or true data. As one example of how they might behave strategically, they could just misreport data. Okay, and they might do that because they care about the outcomes, for example. Okay, another big concern is privacy of this data. So learning algorithms traditionally weren't designed with any sort of privacy in mind, but we often want to now redesign them or add this in because people care about this data may be sensitive or private in some way. Okay, and there's this whole field of differential privacy, and I'll talk a bit about that. Okay, a final aspect, but one I won't get to today, is this idea of fairness for decisions. So the decisions that the algorithms make affect people in certain ways, and the traditional approach of just trying to get high accuracy may have ethical problems when they're put in a context of people. So it's a really interesting area. There's this whole idea of fairness in machine learning, but I won't get to that today. So instead, I'll be talking about projects from these first two categories. Okay, so the outline for the talk. I'm going to tell you about a project dealing with strategic behavior in machine learning, so how to do some learning in a situation where agents are manipulating the data. We'll spend more time on that, and we'll spend a little time talking about challenges that come up when we try to do private machine learning, and a project about sort of translating theory of machine learning, of private machine learning, into practice, and some challenges that arise. Okay, and then some stuff on future directions. So that's the outline. Please definitely stop me. Questions, discussion would all be great. I'd rather have some really interesting discussions here and have a little less time here, if there are interesting questions to talk about. Okay, good. So here's my overall picture of learning algorithms, or algorithms in general, in societal contexts. And for this first project, I want to focus on the strategic behavior aspect. So this question of how do we do learning when these people are being strategic about the kind of data they give to the algorithms. Okay, and so we're going to look at a particular setting, and I want to motivate it with an application, an example of detecting credit card fraud. Okay, so a high-level example, but imagine that over a series of rounds, agents make a transaction and the system sees some data about this transaction. And it wants to know if that's a fraudulent transaction or an honest one. Okay, and you can think of maybe some feature vector as describing the transaction. So maybe there's a vector of real numbers or something. Right, and so the system is going to classify it as being honest or fraudulent. Right, and it has some classifier. I'll be using beta for that. Okay, and eventually the system will learn what the true status of that transaction is, let's say. And in fact, let's just simplify things down and assume it learns very quickly, like immediately, if it was an honest transaction or if it was fraud, because it gets feedback from the account holder. Okay, and then it wants to update and learn better classifiers based on this feedback. Right. Okay, so what's the big challenge? So the challenge is that the fraudulent agents in these systems are going to be responding to the classifier that you pick. Right, so that's why I put this hat on top of xt to denote that this feature vector we're seeing, or this transaction we're seeing, may not be sort of the truth that these fraudulent agents would like to have purchased, for example. So if there weren't some spam feature, they just purchase whatever their favorite thing is. But they're going to be, instead of spam, I should say fraud detection, right? If there weren't fraud detection, they just purchase whatever they want. But they're going to be responding. So depending on what the algorithm's classifier looks like, they're going to be buying things in such a way to try to evade the classifier. Okay, so they're going to choose these transactions strategically depending on what classifier you're deploying in the first place. Okay, so here's a picture of what that might look like. Okay, so if you picture each of these transactions as a point in space, we're modeling it as a point in R2D, then you might have all these blue points representing honest transactions. And these red points, I want you to think of these as the transactions the fraudster would make if there were no consequences. Right? So they'd like to buy, let's say, like chocolate ice cream, or they'd like to buy a boat or whatever. Okay, but they're not going to necessarily get away with that because there's a fraud detection scheme. In particular, if we had all this data, we could deploy some classifier, right? And it might not be perfect, but it would classify honest transactions from fraud, and it would catch most of this fraud. Okay, and yeah, there are obviously some mistakes. So I had a fun incident where my credit card was declined making a purchase. And the location was the city I was living in, and the purchase was running shoes. So I really don't know, that's like, if you know me, that's like most of what I spend my income on. So I don't know what was, yeah, these things aren't perfect in practice. But, okay, but life is even harder because if the fraudsters know that this is the classifier you're deploying, and let's say in the worst case they know or they have some good idea, they're going to be responding and modifying their transactions. Okay, so what you're going to see is going to end up looking more like that, right? So maybe instead of chocolate ice cream, you have to buy strawberry. Maybe instead of a boat, you have to buy a kayak or whatever. But you modify your transaction in some way to try to increase your chance of getting past this filter. Okay, and so the filter has to be designed, this detection classifier has to be designed with these reactions in mind. Okay, and so this will lead to some, in game theory, the idea of the equilibrium, right? That even knowing that fraudsters are best responding, you want your classifier to be the optimal thing. Okay, so this is the perspective people have been taking. So there are a couple papers on this problem. Let me tell you a bit about the approach that they take. So at a high level, they'll say, suppose we have a bunch of data drawn maybe IID from these populations. Some of it's honest, some of it's fraud. It's all labeled. And usually these papers will suppose they know the preferences of the fraudsters. So for example, one assumption might be that there's a vector or direction, and the fraudsters all want to modify that direction or something like this. Okay, and so using that information, they can compute this classifier that does well, even given that they're best responding, the fraudsters are best responding. Okay, so given it, learn some hypothesis, some classifier, and it should do well. Okay, so the work I'd like to tell you about is going to try to weaken some of these assumptions. So one thing we want to think about is an idea of agents arriving online and without having necessarily a distribution. Okay, so if you're familiar in machine learning, often there are these two paradigms. There's a IID data and then predict well on that distribution. But we instead want to think of this worst case possibility. So some transaction just arrives. It's not necessarily from a distribution, but in the long run, we'd like to perform well. And so we'll have to use some notion of regret, which I'll tell you about. Another one is we really want to think about these agents, especially the fraudulent agents, as heterogeneous and different. So they don't necessarily all want the same thing, right? One might want ice cream, one might want, to sail across the river or whatever. And a final important point is that we didn't want to assume that you can see the preferences of these fraudulent agents. So we don't necessarily know what they want. We just see the transactions they tried to make. Okay, so we maybe saw them buying strawberry ice cream. We'd like to try to infer from that, did they actually want chocolate, but they modified it because of our classifier? Or like, do they actually like strawberry? And how can we use that to design better classifiers? Okay, I hope that point makes sense. Okay, so that's the high-level goals. Okay, so the paper is called Strategic Classification from Revealed Preferences, with some wonderful co-authors at Penn or formerly of Penn. Okay, and yeah, there are three aspects to it that I'd like to discuss with you. So the first is, how do we model these aspects that I just talked about? Okay, so we have this idea of online arrivals and limited feedback or limited knowledge about the agents. And then how do we actually, what should we be shooting for? And I think there's an interesting question there, like, how do we measure how well we're doing? And I'll explain why it's not super clear. And then finally, how do we actually try to solve the problem? And for this talk with you today, I just want to spend a lot of time on these because I think they're really interesting, and just a little bit of time on our solution relative to maybe a normal outline. So it'll turn out that we can reduce to known algorithms, or at least leverage them very heavily. But we put a lot of thinking and effort into this modeling questions, and I think that's also really interesting for where to take future directions. Okay, so questions so far? I'll define the model next. Okay, awesome. Okay, so in the fraud example I gave you before, you already saw basically the model. We'll make it a little bit more precise. Okay, so each agent that arrives, so they're either a fraudster or an honest agent, and they have some, what I'm saying, true features, which is the transaction they really want to make. That's what we're thinking of it as. Okay, and they have some true label, which is, let's say, 1 if they're honest and -1 if they're not. Okay. And finally, we assume they have some utility function, which is measuring what's their utility for facing this classifier beta, or this system described by beta, when their true purchase that they'd like to make is X, and they make a purchase X hat. Their features that they present to the classifier are actually X hat, so they've modified it in some way. Okay. So what is this trying to capture? Well, their utility intuitively has some trade-off, where if they're getting classified as fraud or spam for certain, then they're not going to get much utility. But on the other hand, if they make some transaction that they didn't want in the first place, and it goes through, that's not all that useful to them either, right? Like strawberry ice cream, right? So apologies to anyone who actually likes, I think I'm safe, okay. Good. So we're going to assume for this work that honest agents don't act strategically in this way. They just make the transaction they want to make. Okay. So they always set this X hat T, this transaction that actually ends up happening, just equal to the one they wanted. They're not thinking about fraud detection schemes. But we're assuming these fraudsters do act strategically. Yeah.
So, but the fraudsters are being myopic or not? Like, think about how my data will poison the...
Yeah, great question. So we assume they act myopically. So we're going to assume that they best respond with this utility function. Yeah.
Are the true features ID, or they're also like just?
Yes. So we're not going to assume they're IID for this. Yeah. I mean, I guess it would cover, or we could cover that case, and you could deduce some result for that. Yeah, good. Yeah, so we do assume that the fraudsters will choose this x hat t myopically to maximize this utility function. Yes, good. Okay, so we have this online model. So there's a sequence of rounds. The system has a current classifier at any time. The agent at that time arrives, and we assume the system observes, okay, this transaction that they made or tried to make, and then it will learn this true label. So for example, if it was a fraudulent transaction, even if they let it through, the person who owned the credit card will let them know that it's being used wrong, and they'll flag it as fraud. Okay, so the system gets to learn the true label for all the transactions. Is that clear? It's okay? Good. Okay, and then we're going to use some loss function to measure how well the system performed on this data point. Okay, so it's a loss as a function of this classifier that you were deploying, or this hypothesis, and then the transaction that was made and the label. Okay, so this is just some function measuring performance. A natural one you might think of is that this classifier is taking in x hat and just saying 1 or -1, honest or fraud. Okay, and then the loss could be a loss of 0 if it got it correct, right? So if it labeled it correctly according to YT, and a loss of 1 if it got it incorrect. Okay, so that's a natural loss function. We won't end up working with it because it's not computationally very tractable. But it's a good one to keep in mind for the model. And by the way, so this model that I'm presenting to you, just as a heads up, is very general. We're going to end up solving some special case with some strong assumptions. But I think it's fun to think about this general case so that in future work people can try to solve more aspects of it. Okay, good. So the data points arrived. The system has some loss. It updates to a new classifier. The next data point arrives. Okay. Okay. Any questions about the model? Yeah.
So it makes sense to me with the credit card and fraud detection motivation to build a model for a particular person that kind of models, what types of purchases they like.
Yeah.
It seems a little bit strange to me to build a model that models what all non-fraudulent people like versus what all people like.
Yeah, that seems fair.
What's the motivation for setting it up that way?
Yeah, so the formalism that at this level I'm talking about can almost even capture that, because this XT could include the cardholder's history. Somehow it can include their location or other things. Okay. So it could probably include all that in this formalism. Yeah, in practice, you might suppose you want to just separate these problems for each person.
So I can think about the data point including a bunch of features of the person and what they're trying to purchase.
Yeah, okay. Yeah, because we know this credit card is associated to this person or something. So the other application we're thinking about as motivation, which you may have heard from my verbiage, is spam detection of emails. So honest people just send the emails they want to send, and spammers would like to send some particular spam email, but it'll get filtered out, and so they try to modify it in some way. And maybe it's less effective, but it gets through the spam filter or something. Yeah, and again, there you can think about personalization versus everyone's data together.
Does the agent know the exact classifier?
Yeah, great question. Yeah, so does the fraudster know the exact classifier that we're using? Right, so in principle, there's no reason they would, right? If you're thinking about credit card detection or spam filtering, there's no real reason that we would publish for everyone to see the exact algorithm we're using at the current time. But we're kind of thinking of that a little bit as security through obscurity, and that's not a good defense to assume that they don't know the classifier. And you might be worried that, if you're thinking about spam emails or something, they send a ton of spam, they can quickly start learning what your classifier is doing at the current time. So this is a sort of worst case assumption where they just know the exact classifier and best respond to it. So we're thinking of it as a sort of worst case security assumption in that way. Question? Other thoughts? Okay, cool. So now I want to talk about measuring performance, and why it's not obvious how to do that, but how regret can be used. So the key idea is that we're assuming that these fraudulent agents are best responding. Okay? So if they're honest, as I said, they just make the transaction they want. But if not, so let's define this function x hat t of beta to be the best response. So the thing that the agent actually does, the transaction they actually make. Right? So for the honest agent, they just make the one they wanted. But the dishonest agent is doing some utility maximization. Okay, so first let's just define our performance. So this would be something pretty familiar and normal in these kinds of machine learning settings. So we're going to take an average over all time, capital T time steps, of the loss that we experienced at that time step, which is measuring how well did our classifier beta t do when the agent played x hat of t of beta t, right? They responded to it, and this was the true label. Okay, so that's fine. But normally, in this kind of model, you look at regret as compared to the best thing you could have done in hindsight. And now there's a small wrinkle. Okay, so it's not really fair to look at all the fraudulent transactions that were made, right, and put them as dots like I did, and then just say, oh, if we had drawn this classifier, we would have classified them all correctly, right? So that's not fair, because if we had deployed this classifier, they would have been modifying their locations to respond to it. So we can't just look at the past data and say something that did well on the past data would have actually done well if deployed. Because if deployed, the agents would have responded. Okay. And so this leads to this idea that, right, we want to compare to the best fixed classifier in hindsight, as we often do in these learning settings. But if we had used a different one, they would have responded differently. So we need to compare to how it would have performed had the agents responded to it. Right? What's the best thing in hindsight, knowing the agents would respond? Okay, so this was our performance. And then this is what opt should look like. And the key point of this discussion is that if we had deployed beta star the whole time, we would have experienced loss of beta star on the agent's responses to beta star, YT. Okay, and so this looks a little bit different than in a standard online learning where you might say, take all these XY pairs and plug in the performance of beta star on those same XY pairs. This is taking into account that the X's would actually look different. Okay, and the difference between these two performances is just called the average regret. Okay, and in the paper we use this term Stackelberg regret. The term comes from Stackelberg games in game theory, where a leader commits to an action and the follower best responds. So in this case, the follower is best responding to the classifier. So this notion of regret you can actually find in previous papers in other literatures, though. So things like security games, and probably if you're looking at like online pricing and auctions or something, they would be using this kind of notion. But although we haven't seen it given a name, but we think Stackelberg regret's a good name.
So it's like, is it still research because of partial monitoring? Like, so I think the price literature, online learning, like this partial monitoring.
Okay.
Like a generalization of bandits.
Okay. Yeah. Yeah. So yeah, and so it is natural if you're thinking about this problem. So it's not surprising that people have defined it in different places. Good. But an interesting point about it is that you can't. Yeah. Go ahead. Sorry.
So then the Y's are also different, right? In the
No.
and performance.
Yeah. So that's important. So
Because the X's are different.
So think of each agent that arrives, each XY pair. They're either a fraudster or they're honest. But they change, if they're a fraudster, they change their X.
They change their transaction.
They change their transaction X, but their Y is still, were they honest, were they not? Yeah. Yeah, and one thing that's interesting about our model is that's really baked in, that like their label is whether or not they're strategic. So that's an interesting aspect.
Do you need any assumptions on like what fraction is fraud
Good question. Yeah, so we don't need assumptions on what fraction are fraud versus not. One thing we tried to do in an extension is perform better if there's a small amount of fraud, and you'll see briefly why. Yeah. Yeah. So yeah, a key point that's kind of interesting is if you just have the data, the past data in front of you, you can't really compute this opt. Like you have to know what these agents' utility functions were in order to compute how they would have responded if you had done something different. And you don't actually know that. You don't know what their utility functions were. You just got to see what they actually did on that day. Okay, but we'll show how to compete with it, how we can have an algorithm whose performance competes with opt, or at least under some assumptions under which you can do that. Okay, and I guess I wouldn't be surprised if everyone knows what average regret is, but just to be sure, the point is that if average regret is going to 0, then your loss per day is approaching that of opt. Okay, so that's good. So you want this average regret to go to 0. If it goes to 0 very fast, that's better. And by fast, I mean with t. So we're often interested in average regret as a function of time. Okay. All good? Great. Okay, so now let me tell you, so I tried to set up this relatively general question. Let me tell you the specific setting that we're able to solve for this paper. Okay, so we have this, we're assuming some linear predictor. So beta t is also a vector in R to the d. And the prediction you can think of as this number, beta.x. Okay, so if it's, you can think of positive means honest and negative means dishonest. Okay, very positive sort of means I'm very confident that this agent is honest. Very negative, very confident they're dishonest. Okay, the loss, so we think about logistic loss, and we can also do hinge loss, but we just focus on those two loss functions. Okay, so this, I guess most people have seen this before, but right, again, this beta.x, this number, right, if it's positive, it thinks they're honest. So if it matches y, if the sign of this matches y, then you have low loss. If the sign doesn't match y, so you predicted positive, but they're actually fraud, then you have a high loss, roughly. Okay, but it's sort of a soft version of 0, 1, or it's trying to be some soft version of 0, 1. Good, and okay, so now a very key assumption that we make, what does their utility look like of these fraudsters? What are they trying to do? Okay, we assume that their utility is the form beta.x, so being classified as more positive is better for them. Right, so the more honest that they're perceived to be, the better. But they pay some cost. So notice this is beta.x hat, right? So this is what the classifier predicts for them. But they suffer some cost for having to modify from x to x hat. Okay, and so they have to trade off these two things. Okay, and we make some assumption on the class of distance functions that are measuring sort of the cost for making this modification.
Why would the distance be time-dependent?
Yes, good. So yes, the reason is that we want to allow heterogeneity among time steps. So an agent today may care about different things than the agent tomorrow. And this is measuring that to say that like the agent today doesn't really mind switching between ice cream and strawberry, chocolate and strawberry. But the agent tomorrow minds very much, so they have different distance functions.
So what's the rationale for this kind of like disconnect that you're modeling one kind of like, you're putting it through the link from one link for one agent, but the other link, the other agent? Is it so that you can...
do you mean so why the honest agents...
linear, yeah.
Sorry, so...
So I feel like the other loss has this, has this kind of hinge-like form.
This one?
Right.
Uh-huh.
Whereas the fraudster's utility is just fully linear. So there's no satisfaction.
Yeah, I see. So maybe it would make sense for their utility to be sort of like the negative of our loss or something. Like the worse we do, the happier they are or something.
Just for technical reasons to make things
yeah, so it'll turn out that this is like very important for our whole approach, this particular form. Yeah, it would be very interesting to be able to solve something else like that. I think one thing to mention though is one thing that keeps this really interesting is that it's not a zero-sum game, which your proposal would also not be zero-sum because of this, I guess. If it's a zero-sum game, I think things are just less interesting because, yeah, it's just, yeah, but. Yeah.
Is this realistic to assume that this is a good utility function?
I guess, that's a great question too.
So
yes.
one reason is to say like, okay, this is the best we can do technically.
Yeah.
Now does this match anything?
Yeah. Yeah. So we don't really know. We don't have a particular scenario where like we looked at these agents and they definitely have this utility. We can try to understand when this would be reasonable. We don't think the answer is never. So we think there are some scenarios. So the most reasonable thing, the first thing you would think of probably could be like a 1, 0. So like my utility is 1 if my transaction went through, so I was incorrectly classified, and 0 if it didn't. That would be maybe the most natural positive thing here. But yeah, go ahead. Well, yeah, so one thing we're thinking about is if the classifier is using some randomization that's proportional to this. So I'll allow things to go through maybe with probability proportional to the certainty of my classifier, then that this actually does make sense as a utility. Could be. But yeah, the main, if you go for something else from this, we don't know technically how to solve it. So it would be great to do that.
I'm not necessarily sure that that's the most natural thing because I think we said before, like it's unreasonable to assume that attackers have a precise knowledge of beta, right? Here it's kind of like also reflecting that it's like the attackers want to be confident about that their transactions will be classified as.
Yeah, thanks. That's something I forgot to mention, but is a great justification. So yeah, if you don't know, but you know that the higher this is, the more likely you are to pass through the filter, then you just try to maximize this. That's some justification.
So I guess it's not obvious to me how this captures just like the inherent value of x or x hat. Like if x is, I don't know, like a 51-foot yacht and x hat is like a 52-foot yacht.
Yeah.
I don't really care. Like they both have incredibly high value.
Yeah. Yeah. So in this project, we're at a very high level of abstraction, and it's not clear what the space, the R to the D space these things live in mean.
But is there a way to, I mean, like some X hats are just going to have intrinsically higher value, or some X's are just going to have intrinsically higher value. Is that, it seems like the only place that can be captured is in the prediction part.
Yeah. Yeah, so, or maybe another, I was going to say, maybe you could just have a coefficient in front that's like how much I like getting it through, but you're right, because I get different utility for different transactions going through. Yeah, so yeah, that might not be captured by this. That's really interesting.
Couldn't the distance metric also include, dollar amount? So,
yeah, so yeah, we can at least make these comparable. Yeah, so you could sort of say, yeah, actually maybe this coefficient can depend only on my true xt, and then the distance is saying like, my distance from 51-foot yacht. Yeah, like value of 51-foot yacht minus something, number of feet. Yeah, so yeah, and I'm glad that we're having the discussion because this is a great direction for future work. Like, what else can you do besides these assumptions we're making is really interesting. Okay, so, and our approach isn't going to work for all DT, but for some relatively large set, especially norms of of x minus x hat. And so this is a pretty general, almost completely general example of the kinds of distance functions we can have. So maybe you have some matrix A, and you take AX, and you take AX hat, and you look at the distance between them in some p-norm, and you raise that to a power. It's actually important for us that this power be strictly greater than 1. The reason for that is actually intuitive. There's this idea of a convexity involved. And convexity is capturing diminishing returns. So if I move this a certain distance away and I move that same distance again, it's even more costly. And we actually need that to get results. Otherwise, you could have this might not have a maximum. You might be able to get arbitrarily high utility by moving farther and farther away arbitrarily. Okay, good. Okay, good. So the main result is under these assumptions, and in this setting that I told you about, we can reduce to some online convex optimization algorithms and use that to guarantee some regret. So let me just really briefly tell you that result and the idea of it. So think of this loss at time t as just a function of the classifier that you chose to deploy at time t. Okay, so you get that by plugging in beta in several spots here. But think of it as one big function of beta. Okay. Well, if we could get that function to be convex as a function of beta, then we can apply things we know how to do, convex optimization. Okay, and so that's what we show is true. And the main tool is using some convex analysis, details of which I don't think are important for this talk, so I'll skip it. But yeah, so the corollary is by applying various convex optimization algorithms, you can get regret that's going to 0 as t increases. With some very fancy one, you can even get, I think, 1 over root t or 1 over t to the 2/3 with better dependence on dimension. Okay, and this is despite, I should emphasize, not knowing exactly what this loss function is that arrived, right? So we don't know this whole, so we have now a sequence of loss functions at each time. They're each different, and we don't know what that entire loss function is because it depends on their utility. We just know that it's convex. And there are convex optimization algorithms that actually work in that setting.
Yeah, so just to be precise, you're talking about like the banded convex optimization, right?
Yeah, I think so, yeah. Yeah. Good. Yeah, and so, sure, well, yeah, so some just quick extensions in future work. Okay, so an extension is you can treat these honest updates and fraudulent updates differently and do a better job with your algorithm. The reason is that when an honest agent arrives, you actually do know this convex loss function because it's just your loss function. If you change beta, the data they gave you is not going to change. So you can compute a gradient, and you can do a good update step. When the fraudulent update occurs, you can't do that, and you have to do something that doesn't use gradient information. If, for those of you who are familiar with such algorithms, if not, it's not a big deal. Okay, so we have somewhat more general agent utilities, and also hinge loss. The ideas are the same. Okay, but there's tons of room for future work. I think it's really interesting, as we've been discussing. So other loss functions, definitely. Other forms of agent's utility, definitely really interesting. And especially if, so our whole general approach here, once we formulated the problem, ended up being to reduce to this convex optimization, which we know how to do in this online setting. So, I mean, one way to push on this is to just say, well, here's another case where we can use convex optimization. Here's another case. To go outside of that, I really don't know, what approach you can take. That'd be really interesting as well. Okay. Yeah, go ahead.
So I guess one thing that makes me slightly nervous about the reduction to online convex optimization is that it actually becomes really crucial that that the attacker is in fact best responding to the real knowledge of your beta, right? And so if they were actually working with some sort of imperfect knowledge about what I'm doing, or if I just, like, one very common thing that goes on in these algorithms is you have your current set of parameters, and because you can't observe a gradient, you randomly perturb it and play. So
Yep.
there is no way in hell they can know what random perturbation I actually applied, right? So
Yeah.
how do I mean, that doesn't...
Yeah, no, that's a
jive.
great point. Yeah, I think that's a disconnect between our model and how you would deploy this in reality. So maybe for the recording, I should say, so the question was, this is really relying on agents exactly best responding to the exact beta we deploy. And you're correct, we're using these convex optimization algorithms that like perturb beta a little and see how the gradient, or see what happens, and use that to guess the gradient. So if agents aren't best responding to the exact beta, including this perturbation, then it's not clear this is going to work. Yeah, I think maybe there can be some way to get around that by, if you make some assumptions about agent utilities, you could guess that maybe the gradient, like locally, you can guess that they won't change too much, and then just use the gradient of your own loss. So yeah, it should be addressable, I would hope, but not in this paper. It's a great question. Anything else? Yeah.
Yeah. I was just trying to think as a credit card fraudster my utility would be, and it seems like it would be like a lot related to the dollar amount of the item, or like the dollar amount you could get from selling it. So probably some things are easier to sell than others. So
Yeah.
so maybe if you could run it, like if it all comes, suppose it all comes down to one number, like the dollar amount that you can sell something for.
Mm-hmm.
Would that simplify what you're doing, or would that fit into the model?
Yeah, would it? Maybe, yeah. I think this is really similar to the previous question about, yeah, like could we sort of, this utility doesn't seem to directly depend on something like dollar value amount, but could we somehow argue that that's a special case where there's a coefficient which is the dollar amount of X?
More thinking the second term could just depend on the dollar.
Yeah. So it seems to me possible. Okay, so we wanted A to be invertible, but if you're thinking of maybe A is mapping these purchases into dollar amounts, okay, if it's mapping down to one dimension, maybe there's a problem with our formalism. But it seems possible, but yeah, I don't want to claim this utility is capturing too much because it's a pretty special form. So I'm not sure. Not sure. Good. Okay, great. So, yeah. So while I have you, I'd like to give you a different example of this machine learning in societal context, which is going to be a privacy-focused example. Okay, and much briefer, of course. Yeah. So, strategic behavior was one really interesting aspect of this idea. Another one that I'm interested in is this idea of, okay, maybe the agents, they don't have a particular concern about what this classifier is doing, so it's not like, it's classifying their own transactions, but there is this privacy concern that it's going to reveal information about my data. Okay, and yeah, differential privacy is a field which turns out to be some very nice theory and also moving into practice for addressing this issue. So I think I can probably guess that everyone's seen differential privacy a few times or many times. So I hope you don't mind. I think I'll just skip the definition. It's actually not that important for the level I want to tell you about this project. The high-level idea is your algorithm should be randomized, and by adding noise or being randomized, reveals very little about the data because a change in one person's data doesn't make much difference in the output you see in terms of probabilities of different outputs. That's the high level. If you know that, then you know enough to follow. So let me just skip this. I think it's fine. Okay, so what do we want to address in this project I'm going to tell you about briefly? So differential privacy, it's pretty well understood and practical, I would argue, for answering statistical queries about a data set. So what is the mean of this data set? Something like that. Or different queries about some complex data. It's even being used in the census, which is pretty cool. And the most basic approach is that, okay, so there's this parameter epsilon differential privacy, If you add noise that has standard deviation like 1 over epsilon, then you're preserving epsilon differential privacy intuitively. So epsilon very small is very private, but lots of noise. So we understand all that very well. Machine learning queries on data is very interesting. So there's more recent work. It's quite active. But I would argue it's not well understood, at least not in the way that statistical queries are. Because the kind of theory bounds we get might be quite loose because we're using these complicated algorithms. Right? So this algorithm is take the true number, add some noise, okay, and then we can analyze how accurate that is. If you're talking about something like a stochastic gradient descent with extra noise added to preserve privacy, understanding how private and accurate that really is going to be very difficult. And often these papers are written by theorists, so who are great, and I love theorists. Okay, but their theorems tend to look like, I should say our theorems tend to look like this. They tend to look like the following. Let's say like you prove some general theorem that says you run our algorithm with privacy level epsilon, and I'll guarantee you an accuracy alpha with high probability. And often you might prove something with a constant that looks like this. More often you prove a constant that looks like this, right? So okay, why is this an issue? Like, I think it's an important idea. So people do this in algorithms, but you put the algorithm in practice and it runs really well, then it doesn't matter. The fact that you couldn't prove a low constant is not a big deal. But here I want to argue it is an issue. So let's say you're an engineer at some data corporation, and you want to run a differentially private, you want to run this algorithm. Well, you have to choose the privacy level you're guaranteeing to people. Okay, and the problem is that this theorem isn't really going to help you that much in figuring out how you should actually choose it. If you want an alpha of 0.01, should you set epsilon to be 100,000? That will guarantee you an alpha of 0.01, but there's no privacy at all, basically. Like, we want epsilon to be around 1 or less. On the other hand, you could get away with setting epsilon to 1 because probably there's all these loose constants in there, but you don't know. It could be hard. And what if accuracy is critical to your system? So you can't afford to take chances. Okay, so this project, this is a paper at NIPS last year with some wonderful co-authors, and Stephen. No, I'm sorry. I'm sorry. That's not true. The most wonderful of them all. So the question is, if we have an accuracy requirement, can we run a learning algorithm that tries to find the most private possible output, right, that we can have, right, without having to tell it what epsilon and alpha to shoot for, or sorry, what epsilon to shoot for? It'll try to satisfy this accuracy requirement, but be really private. Okay, and so the setting, it's what we call empirical risk minimization. So you just have this data set, and you have a loss function, and you just try to find a hypothesis that minimizes loss on the data set. Right. Okay, so I'm just going to give you an example of the idea that we're deploying, and that'll be about it for this project. So that'll be about all I'll tell. Okay, so one kind of private algorithm is called output perturbation. You compute the true output. So for example, this is a hypothesis, let's say, like a classifier or something, that you found by doing empirical risk minimization on your data set. Okay, and now you add a bunch of noise to all these numbers, and now it's private. Okay, and the difference here is that we're going to use random walks to add this noise. Okay. So if you run a random walk for a certain length of time, you've added a certain variance of noise to each number. And that's fine, and you get some output. Okay, but now the key idea is to check how accurate this is. And if it's not accurate enough, right, you wanted a certain accuracy level, then we're going to have to improve the accuracy somehow. Okay, so there's this idea of this step called interactive above threshold that checks the accuracy, sorry, that I'm not going to talk about, but you have to worry about leaking privacy when you do this. Okay, but let's suppose we check the accuracy. If it's not accurate enough, the idea is to rewind the random walk. Okay, and that's the key idea. we got it from a similar idea in a statistics paper on privacy that kind of does the reverse of this. So now let's just rewind to here. Okay, that's on average less noisy. Check the accuracy. Is it good enough? If it's not accurate enough, so if this hypothesis is not predicting well enough on the data set, rewind some more. Okay, eventually, as you approach the left, you're going to approach the true best possible hypothesis. So you will approach something that's accurate enough, right? And that accuracy requirement will tell you when you can stop. Okay, and now it's kind of late in the talk, but maybe I can try to convey this intuition for why this is good. So the key idea of why this is good from a privacy standpoint is what you'd worry about is this process, this interactive process of compute some output, check its accuracy, and so on, is leaking lots and lots of privacy. Right? So you'd worry that all these outputs are leaking information about the data set. You can actually analyze it as though in the worst case we published all these outputs. That would leak possibly lots of information. Okay, this turns out not to be true because of the random walk. So the idea is this noisy estimate here. Okay, so if you see this noisy estimate, you're inferring something about the data. But once I reveal this less noisy estimate, that noisier one does not give you any more information about the data. Why? Because of these random walks. Right? So if I tell you this number, and you're trying to guess or infer, this thing which is private, this number will not help you at all. It's independent conditioned on this one. That's the idea of the random walk.
So this is why it's important that you rewind rather than doing a fresh, smaller.
Exactly, yeah. So that's why we save the result of this random walk secretly and rewind it instead of just try again with less noise. Yeah.
And you can't go the other way. Like if you suppose you have plenty of accuracy, but you want more privacy.
Yeah. So that's tough to reason about because, you've leaked some sort of information just from the fact that you decided to increase the privacy, like increase the noise. And that information you leaked depended on this very accurate thing you computed, which was very non-private. I don't want to say it's impossible, but to analyze is really difficult. So we don't know if
you have to start, or at least in your algorithm, you have to start with
the very private thing and then
way more noise than you think you need.
Yeah. Yeah.
I guess I missed a little bit of motivation or background on when do you I was thinking like this whole thing is like done inside a private box.
Yes, that's true. That's true.
You're kind of assuming that every check on the right-hand side leaks information as public.
Yes.
Can you give me a scenario where that is true?
Yeah, so it's not necessarily true. It's more about how we know how to analyze these things. Often in privacy, we have a very hard time understanding how much information is leaked. And so we'll say, well, okay, even if we publish this entire thing, we can still show, and we don't know how to prove a better privacy bound for the thing that doesn't publish it. It could
publish the end result, right?
Yeah, so in our analysis, you could have just published this hypothesis and the fact that it wasn't good enough, but you don't say what its accuracy was, you just say not good enough. Publish this one, you say not good enough. Publish this one and say that's our final.
Because given the final one, all the previous ones are useless.
Yeah, and so it's kind of getting into, is it just analysis or is it actually what you're doing? Yeah, it could be that we're just not good at analyzing. Yeah. Okay, so that's the key idea for this project, basically, that I wanted to convey. But you can use this trick in other places as well, or for lots of algorithms. Yeah.
So for my question, will also connect to Alex's previous question. So if I don't worry about, say, I only publish the final result, and I don't worry about leaking information about like earlier noisier results.
Yeah.
Do I gain anything for keeping the random work versus get a fresh randomness to rerun the thing?
So if you care about privacy loss, this is going to be better than doing a fresh noise each time. Well, again, we're not sure how to analyze like where you're trying to keep things secret, but Yeah, yeah, yeah.
Isn't there a little bit of a leak of information just from knowing the fact that it wasn't close enough to the
Yes.
true private valuation?
Yeah, so the fact that this thing's accuracy was not below the threshold tells you something, and that is analyzed in this part of the puzzle that I didn't talk about. So in particular, like, you don't want to make these like billions and billions of checks, because that will add up, but you get some sort of logarithmic dependence on the number of checks, so it's not too worrying. Okay, so let me just recap this and finish up so we don't go over. So the general idea of this project is take some known algorithms for differentially private machine learning and just apply these two tricks. So these accuracy checks that I didn't talk about and this noise reduction that I did. And then these algorithms, you give them some accuracy goal, and they try to give you an answer that's that accurate, but as private as it could be. Or that's the idea. Okay, these are important. Like, we're lower than the others, and that's good. Theorist, whatever. So some quick future directions. Yeah, strategic behavior and learning, and not even just learning, but this paradigm, I also think of like prediction markets in this paradigm, right? Like, there's information out there, we're trying to gather it and make predictions. So this is an area I think this general question is super interesting, and there's tons of directions. From both practice to theory. Privacy, I feel that privacy is moving towards practicality and applications. Like, there are interesting theory questions, but they start moving farther and farther away from practice. But there's a lot of like very practical questions that we need help with, so that we can deploy privacy to help people. And it's like the time to do that. Fairness, which I didn't tell you about any fairness projects, but I think it's kind of the opposite. Actually, we're really struggling in theory land to get a handle on fairness. And initially people sort of expected some sort of one-size-fits-all definition, which is what happened in privacy almost. And now we're seeing that's not really possible. And yeah, there's tons of interesting directions there too. Okay, so I have like some very high-level closing slide. I think it's really important when both thinking theoretically as well as in practice to be thinking about the value and structure of information in these problems. That's really important. So the information agents give us is really valuable, and because of that, it's susceptible to manipulation and so on. I think it's important that these systems respect these issues like privacy, fairness, and also strategic behavior. I think it's interesting to take the perspective that agents have the right to be strategic and act on their own behalfs, and so we should design things that work well, taking that into account rather than slapping them on the wrist for being strategic. Okay, and this issue of data ownership and control I think is really important, and I hope that we can do some research in our communities to understand it better. So, okay, that's it, thanks.